So we're going to clean the lenses with lens paper. Start by taking the lens caps off. And so you always want to make sure you use lens paper or something similar. Kim wipes don't work for this because we want to make sure we're not scratching the optical surfaces. So right now, Leigh is tearing off a piece of lens paper and she's being very careful not to get her finger oils on the side of the lens paper that's going to touch the optical surface. And she's putting isopropyl alcohol, also known as rubbing alcohol, on the lens paper. She's going to very gently wipe the optical surfaces, being careful not to grind any hard substances that might be on them into them, causing scratches. And the alcohol, when it's done, is going to evaporate on its own fairly quickly without leaving residue. If you're really concerned that it's dirty, you can do water first, but that should be good. So we're going to talk a little bit about connecting the BB9 today. This is our big fat BB9. We're going to just do a bench test of it. So we have our 13.8 volt power supply. We do anything from 7.5 to 15. This is what we have here. We have our cable. One end is a 6-pin DIN. So there's 6 metal pins go in here. This is the female end. The other end we have our 2-pin power supply and our 9-pin serial. So all I'm going to do is just plug in the 6-pin connector to the BB9. I'm going to close it off. And I'm going to plug in the serial connector to the computer. And I'm going to plug in these 2 pins to the power supply. Red to red, black to black. And we can take the caps off so you can see better. And we'll turn it on and start the disco lights. So BB9, we have 9 wavelengths, 3 heads, each one does 3 wavelengths. We have the blue head starting at the lowest wavelength at 412, highest energy light, going on to green and yellow on this head, and red and infrared on this head. It ends up at 880 at the very highest wavelength, which is the near infrared, and you can't see it. We use this to try and match up as best as we can with the AC9 wavelengths. 880 is not an AC9 wavelength, but we have it here. And we can have multispectral backscatter. Okay, so the BB9 sensor, as we said, it records in 9 wavelengths and has 3 on each head. And you can see the lights really clearly. You can see here's one blue light, here's another blue light, and the third blue light over here is really hard to see because it's in ultraviolet, is over here. So you might be able to see it in the camera, I'm not sure. But there are actually 3 sensors as well, and they all lie in a straight line. So here's one right next to this light, here's the next one right next to this light, and here's the third one next to the yellowest of the blue lights. And that's true of all the heads. The sensors are all in a straight line. So when you want to do a dark count in order to make your corrections, what you do is you get black tape, and you want to take the tape and put it in a straight line over all the sensors on each head, as Leigh is doing right now. And so you don't have to worry about covering the lights. What you're most worried about is covering the sensors. There you go. So there we go. Now that all the sensors are covered, when we collect data, we're going to get whatever the dark count is, and we're going to subtract that from the counts we read when we're collecting data. And now to take them off, you just tear each piece of tape off and you clean it as before. And you just want to be very careful to make sure that there's no residue left. If you put alcohol on it and rub it, and you can still see the lines of where the tape was. That means that you've left residue behind and you need to do it again. To find out which COM port you're using, first you want to go to your device manager. By typing device manager in your start menu. Wait a moment for an option to come up and click enter to enter your device manager. Expand ports to see what COM port your adapter is connected to. In this case, it's COM4. Start hyperterminal. So now I'm setting the COM port to 4 as it was before, and the bits per second to 19,200. And as soon as I connect, and if it's on, I don't think it is, once I turn it on, I should start to get data after it boots up. Now at the moment, it has black tape on it, so I'm getting dark counts here for 412, here for 440, here for 488 on both lines, here for 510, here for 532, here for 595, here for 650, and here on these two lines for 715, and finally for 880. With our BB9, they're usually around 50 counts per channel. Now if I want to record the data, all I have to do is click Transfer, Capture Text, and choose a name for the data I want to capture. I'll call it BB9 Dark right now. Click Start, and everything the BB9 sends me will be captured. You can also use this to collect data, though you'll probably be using something like a DH4 to make sure you capture text indexed with other things.
Hello. So now I will try to explain how we convert from raw data from the instrument to VSF values and how to correct for seawater, how to correct for path length, and how to convert to backscattering. Hope you enjoy. We need to convert from raw data in counts to volume scattering function. To doing that, we need to subtract what we obtain from the instrument. We need to subtract the dark counts, which are measured in the calibration process. Basically, you put a black tape and in the instrument, in the sensor of the instrument, and you take measurements. Then we have to apply a scale factor to convert from raw data to VSF units. The raw data looks like this, in which we have many columns. The first column in this case is a code from the instrument, then there is some internal parameters of the instrument, but the most important is the data that we have wavelength and measurements. In this case we had 412 nanometers and then the measurements in counts at that wavelength, then 440 and measurements at that wavelength, and so on until we go to 880s nanometers, and then we have the measurements. After this, we need to take in account the seawater. For that, we need to subtract the seawater VSF from the VSF, and we will obtain particulate VSF. For that, we use the MATLAB script created for Xiandong Shan in 2009 called Beta CS CW and ZH 2009. And for more details, you can Google it, and it's available in the internet. So after that, we need to take in account the absorption producing along the path length. For that, in this case, from the user guide of the instrument, in this case is the Eco BB9 user guide from WETlabs. We apply the following equation, in which we multiply for an exponential to the path length L and the absorption that in this case we use from an ACS instrument, the absorption coefficient from ACS instrument. After that, once we have BSF, we would like to obtain backscattering coefficients for particles. For that, we use the method described for Bose and Peugeot in 2001, in which we apply a factor 2 pi for a chi factor, with in this case 114, and we convert to a backscattering coefficient for particles in units of 1/meter. So as an example, we create a MATLAB function in which we take in account all the calibration process, and we call in this case BB9 Carl for stand for calibration, and then we apply the different factors. We extract the dark counts, and then we use the function to subtract the seawater BSF. Then we apply the backscattering equation to finally convert to backscattering. As an example, we have here the BSF for the different wavelengths, and this is for downcast for different depth, and also then we apply all the equations to convert for backscattering coefficients for particles, and we obtain these curves. Another form of show the data could be this figure, in which we have for different depths we have the spectral shape or the BSF. Hope you enjoyed the video, and thanks.